In the previous section, we discussed what a sequence was, which is an infinite list of ordered numbers, numbers that are ordered by an index called n, or any variable we want. We can define those sequences using an explicit formula where each of the terms is defined as a function of the index of the terms. We do like to work with explicit formulas. But we could also write our sequences as recurrence relationships, or sometimes they are defined as recurrence relationships, where the terms, each individual term is defined based on the previous term. So that's where we're starting at, working with sequences. We played around a little bit with them in the last section, and we even started to consider what happens to those sequences as n, the index, goes to infinity. So let me get this on the screen. And now we're going to officially start to define the limit of a sequence. So let's consider what happens to each of the terms, a sub n, as the number of terms approaches infinity. Very, very similar to looking at limits of functions as x is approaching infinity. We say that a sequence converges to a limit L if that limit of the terms, a sub n as n approaches infinity, equals L. If that limit exists, then we say that the sequence is converging, meaning the terms in the sequence actually approach a finite value. A sequence that does not converge is said to diverge or be divergent. Now, we do have an epsilon delta form of this definition. I'll show that in just a second, but let's just look at a little picture. So if we have a sequence, we also talked about graphing sequences in the last section on the previous videos, but if we think of this as being n and a sub n and plotting our points, so if this is 1, 2, 3, and 4, and we plot all of our points as n, a sub n, so we plot those points to graph the sequence a sub n. Let's just suppose that we get something, let's call that L, and we're plotting these points, and let's suppose that they are, as n is increasing, they are approaching this value L. So we're watching, we could take a highlighter here, we're watching those terms approach a finite value. That is what we would say is a convergent sequence. It is converging, the limit as n is approaching infinity of those terms are approaching L. Now, what would a divergent sequence look like? Well, that can happen in a variety of ways, and so let's draw a couple of those. So let's just say we were plotting points for the sequence, ordered pairs for the sequence, and let's just suppose they are increasing without bound. They just continue to go up, up, up. I'm running into my other sequence there, and they never approach a finite value. They're increasing. This is what we would call increasing without bound. I ran into my other function, but it was not flattening out. It was not approaching. I ran into my other graph, sorry, not function. This is what we would say is a divergent sequence. And we will want to know why sequences diverge, and so we can use our limit tools and our limit technology to say that the limit in this particular case of this sequence that I've graphed is approaching infinity, meaning it's growing, right? Anytime we use infinity there, I just dropped my eraser and it erased part of my words, sequence, that it is growing without bound. That's what it indicates when we say that something is infinite. So that's one way that we could have a divergent sequence. Another way that we could have a divergent sequence is through some kind of oscillation. We could look at something, if we were graphing it, and let's just suppose we were plotting it and it was doing something like this for each of the terms. If we plotted the terms off of their index and we got something, I don't know, it was doing something like that. And if we were to highlight what's happening with those terms, if we were to see kind of this infinite oscillation. So again, when I'm graphing each of these, I'm plotting the n and a sub n terms. This is n and a sub n. In this case, we would also call this a divergent sequence. And in this case, what's happening is the limit as we're approaching infinity of a sub n just doesn't exist. There's oscillation. Specifically towards positive and negative infinity, growing without bound, but in both directions. And so, those are just a couple of reasons why a limit of a sequence might not exist, and of course, a visual of one where it does exist. So it's convergent if it approaches a finite value and divergent if not. And so here we actually have the official epsilon formula, and this is what it says. It's saying to us that consider what happens. I'm trying to find my cursor here. Here we go. Oh, found it. There it is. It says, consider what happens to a sub n as n is approaching infinity. And this is very, very similar to looking at functions and observing the limit as x is approaching infinity. So we say that a sequence is said to converge to a limit L if for any given epsilon greater than 0, there exists a positive integer n such that the distance between, that's when we take absolute value of a difference right here, the difference between the terms in the sequence minus L, a sub n minus L, that's the distance between the terms in L when we put it into absolute value, is less than epsilon whenever n is greater than or equal to capital N. And then we can say that the limit of a sub n as n is approaching infinity is equal to L, or we could even use our arrow notation, a sub n approaches L as n goes to infinity. A sequence that does not converge is said to be divergent. And so here you can actually see two examples of convergent sequences. And if we think about drawing in epsilon bounds here, so given any epsilon, if we take L plus epsilon, and L minus epsilon, and we draw in those epsilon bounds, we can see that eventually, I'm going to highlight that neighborhood, we can see that eventually all of the terms of the sequence will be, it starts about right here. This would be where we would let our positive n be. And then notice that all of the terms in the sequence for all of the n's greater than capital N, all of those terms in the sequence are within an epsilon neighborhood of L. And we can see that that sequence is converging in on that value L. And we can show that by, of course, we could shrink this neighborhood down. We can make it smaller and smaller and smaller because the statement up here is for any given epsilon. So we can make that neighborhood as small as we want. We would just have to push that capital N out further if the neighborhood got smaller. And in a very similar way, you're seeing the same sort of thing happening here, given any given epsilon. Notice on this particular one, L plus epsilon and L minus epsilon. On this particular one, the terms in the sequence are actually oscillating around their limit. They're going above and below, but they are squeezing in and coming down to their limit. And so you can see, basically, it looks like the way I drew, that one's right on the bound. So maybe right about there would be my capital N. And for all the terms beyond that, based on the little epsilon I generically drew, for all the terms greater than that, we would have them within that epsilon neighborhood of L. Okay, so that's our official definition of a limit of a sequence, and now let's get into the nitty-gritty. How do we take these limits? And the way we're going to take these limits is with function properties and using all of the tools that we have from Calculus 1 for taking limits of functions. And we have this very, very handy theorem that says that the limit of a sequence using a functions limit says that if the limit of f of x as x approaches infinity equals L, and f of n, where n is all the integers, is equal to a sub n, the terms in the sequence for all of the integers, then the limit as n approaches infinity of the terms in the sequence a sub n will be equal to that L value. I like to give this a little name. I call this the connecting the dots. Because when we plot a sequence, we are plotting, and you can see that on this little graph right here, we are plotting a set of points, right? The x value is the set of integers, and the output value is the terms in the sequence, and we plot all of those. And so what this allows us to do is it says that if a sub n is equal to f of n, a function can be representing each of the terms in the sequence for all of the integers. That simply allows us to come in here and say, let's connect the dots. I've been doing it with my highlighter, but it says, let's connect the dots. And then rather than looking at the limit of those dots, we can look at the limit of the function. And it does give us the ability to use all of our function tools for limits. So it is extra helpful. So let's give it a little star. It allows us to use all the things we know about functions when we take limits, as long as we can write the sequence in terms of its function. All right, so let's associated function, I should say. So let's take a look. Let's determine if the following sequences converge or diverge. If they are diverging, we're going to go ahead and explain why. So what that previous theorem allows us to do is it allows us to take this and say, let's think about it, right? In my mind, my little thought bubble here is saying, let's think about f of x equals x over 2x plus 1. When I plug in n, f of n, that would be exactly equal to 2n over 2n plus 1. So that allows me to use my connecting the dots theorem. So this allows me to take the limit. If we want to know if this is converging, this allows me to take the limit of the terms in this sequence, n over 2n plus 1, as n is approaching infinity. And it allows me to use all of the tools I have from taking limits of functions. Now, we do have to think about this. There's actually a variety of ways that we could do this particular one, because this ends up being, if we just plug in infinity, the numerator is approaching infinity, as is the denominator. So you get something of that nature. You might first think, let's apply L'Hopital's rule, but there's also some elements that we discussed back in Calc 1. We could think about the fact that it's a rational function, and we could use the fact that the degree of p is equal to the degree of q, or we could even use some algebra, and just a reminder of some of our limit tools. We could also use some algebra and just divide by the highest power in the denominator, which is n. I was looking over there for a second. The highest power of the denominator. So, right, we've got lots of tools. I'll go ahead and use L'Hopital's rule, but we don't have to. We have other tools for doing this. But if I use L'Hopital's rule, then the limit of 1 derivative of the top, limit of 1 over 2 derivative of the top over the bottom, as n approaches infinity, is simply a constant, and this is going to be 1/2. So we would say that this limit converges. The terms in this sequence are approaching 1/2. And I actually have a visual in Desmos that I want to show you, so I'm going to pop over to Desmos and show that visual for this one. Okay, so here is my Desmos, my coding. I put in the sequence that we're looking at, and I even wrote in the function that we are likening it to. We're saying this sequence is connected to this function because f of x equals x over 2x plus 1, if I plug in n, would give me the terms in the sequence. And so what we're going to do first is just see the sequence being plotted. So we'll see purple dots being plotted. Again, I have this out to about 65, so it looks like I actually have it, so I could go out to 100, but 65 will be good enough. And then notice the scale right here is intense. So if I hit play, we're going to go ahead and see those dots that are representing the terms in the sequence. And what you can do right there is you can see that they are approaching 1/2, as we have shown with the limit. They're approaching 1/2 right there. If we were to actually use that theorem that we're applying when we take the limit and graph that, like connect the dots, take that function that we're working with and think about connecting the dots, you can see the limit of that function is approaching 1/2. Therefore, the limit of the terms in the sequence will also approach 1/2. So it's kind of a nice way to visualize what we're doing in the calculations. Okay, let's take a look at another one. So this particular sequence is just the sequence that is the switch with no other component to it. So if I were to start to write this out, let's just write out what this actually looks like. If I were to write this out, when n equals 1, this would be -1, n equals 2, it would be +1, -1, +1, -1. We explored the switch in the previous section, but you can see right here that this is oscillating. I won't go over to that graph to graph it, but let's take a look at what's happening here. 1, 2, 3, 4, 5, 6. If we were to plot these points, we're at -1, +1, -1, +1, -1, +1. If we were to actually think about right here what's occurring, this is going to, I'm trying to grab my highlighter here, this is going to oscillate. You can see this is just going up and down and up and down and up and down forever. And so what we say here is if we try to take the limit as n is approaching infinity, of -1 to the nth, this limit does not exist. There is oscillation between positive and negative 1. And so there's our justification for why this sequence is diverging. It diverges because we have that oscillation. So we have that switch, and it's continuing to just go back and forth between negative 1. It's not getting closer and closer to a single value. You can have oscillation where you oscillate in on a limit, but in this case, we're oscillating just back and forth between positive and negative 1. Okay, here's another example, and we could write out a couple of the terms in the sequence if we wanted to. We got 1 over e, 2 over e squared, 3 over e cubed, 4 over e to the fourth. And I am looking at that, and I'm looking at the denominators, and we're raising ever increasing powers on e. The numerator is also increasing, but one of the things we're going to talk about in this section is the growth rates of the numerator and denominator, and this is definitely bottom heavy is one way to think of it. But what can we do here? If we want to consider if this converges or diverges, we're going to take the limit as n is approaching infinity of n over e to the n. And that does give me that infinity over infinity, which is indeterminate, but it opens the door for L'Hopital's rule. So we can use L'Hopital's rule here. The limit as n is going to infinity. When we take the derivative of the top, we get 1, and the derivative of the bottom, we get e to the n. And this becomes 1 over infinity when I take the limit, which is 0. And so we would say that this guy is converging to 0. And you can, again, as I mentioned when I first wrote out those terms, you can see that the bottom is increasing at a much faster rate than the numerator. Okay, let's take a look at this problem. Notice on this problem that we have a switch, which means we know that the signs of the terms are going to be alternating. So what do I do? If we've got a switch on it, one of the tools that we can use is we can consider what happens to the absolute value of n. We can consider the sequence of terms, the absolute value of n, and consider what happens to the limit as n is approaching infinity of the absolute value of n. That can give us a starting place, because how are we going to evaluate it when we know that it's alternating? Well, if we could write out a couple terms and kind of evaluate and think about what's happening, or we can consider the absolute value. So when I take the absolute value here, what's nice about the absolute value is the absolute value can run inside of the switch, and so then we're taking the absolute value of negative 1 to the n. When we take the absolute value of n, it is just n, because n is positive, and the denominator is also positive. And when we take the absolute value of the negative 1, that just becomes positive 1. And so the absolute value here is n over 2n plus 1. And we can take the limit of that. The limit as n is approaching infinity of n over 2n plus 1. We actually already discussed this. We can use L'Hopital's rule, or we could use the degree. Here I'm just going to write the degree of p equals the degree of q. This was one of our examples just a minute ago. It is 1/2. And so the limit of the absolute value of the terms is, so remember this was the absolute value, is approaching 1/2. Well then, what happens with the switch? Well, what happens with the switch is that we're still going to approach 1/2, but we're going to be approaching 1/2 in such a way that it's alternating between positive 1/2 and negative 1/2. The terms are going to alternate between approaching a positive 1/2 and a negative 1/2. And so what happens is looking at my index right there, all of the odd terms are going to be approaching negative 1/2. So all the odd terms, so if we look at A3, A5, A7, A9, as we head out towards infinity, the odd terms are going to approach negative 1/2, whereas the even terms are going to approach positive 1/2. But that creates oscillation. So even though the absolute value is 1/2, because we have the switch, we are getting oscillation. This is going to diverge by oscillation between positive and negative 1/2. We're going to oscillate between positive and negative 1/2. If we kind of think of the terms, what's going to happen is if this was 1/2 and this was negative 1/2, we're going to be approaching those, but splitting like this. So we are going to approach those values, but we're going to be oscillating as we go. So it's going to be something like, so we're still going to be approaching those values, but we're going to be oscillating as we do it. Okay. All right, let's take a look at another one to say this is our sequence. So if this is our sequence, we want to take the limit to determine if it converges or diverges. We want to take the limit of the natural log of n cubed plus 1 minus the natural log of 3n cubed plus 10n. And if I take the limit of each of those and let n approach infinity, I get the natural log of infinity, which is infinity, minus the natural log of another infinity, which is infinity. And this is an indeterminate form. Now, it's not one of the forms that I can apply L'Hopital's rule to yet. I've got to get it into a form of infinity over infinity or 0 over 0, right? Anytime we have one of those other indeterminate forms, we got to get it into a form that's a quotient so that I can actually take and apply L'Hopital's rule. So I come back and I think, how can I bring this into a quotient? Well, I see that minus, and I'm going to use some rules of logs here. And using rules of logs, I can pull this into a single log. That's the natural log of n cubed plus 1. Since it's a minus, it becomes a division, 3n cubed plus 10n. And now I'm taking the limit as n goes to infinity, but the natural log is a continuous function, and our rules of limits allow me to come inside of a continuous function and consider the limit of the interior. Now on this one, again, I have all of those possibilities. It is now infinity over infinity, and I can use L'Hopital's rule. I can use the fact that the degree of P equals the degree of Q. So when we have the same degree powers, it's going to be a ratio of the lead coefficients. Or I could even divide top and bottom by 1 over n cubed. Those are all my possibilities for finding this limit. So I'm sort of thinking about that once I take a look at this. And on this one, let's go ahead and just use the degree of P equals the degree of Q. And so it's going to be a ratio of those lead coefficients, 1 over 3 when I take the limit. And we are inside of the natural log, so it's the natural log of 1/3, which is a finite value. So this definitely converges. So we've got convergence here. Okay, last example. I'm trying to get a lot on this video so you have lots of examples to work with. So let's think about what we're doing here. So we've got n plus 1 factorial over n factorial. So, let's just think about what this looks like if we expand. So that's 2 factorial over 1 factorial. The next term in the sequence would be 3 factorial over 2 factorial, 4 factorial over 3 factorial, and so on and so forth. But factorials, when we have factorials like this sequence could be simplified. If we have a factorial over a factorial, we can think about if there are any common factors in their expansions. So n plus 1 is n plus 1 bang, or n plus 1 factorial is n plus 1 times n minus 1, all the way out to the factors 3 times 2 times 1. And the denominator is starting at n, so it's n times n minus 1, and all the way down n minus 2, all the way down till we get to 3 times 2 times 1. And so what ends up happening here, we could see that actually with the numbers up above. If let's go one more out, because let's see it with slightly higher numbers, 5 factorial over 4 factorial. If we write that out, that's 5 times 4 times 3 times 2 times 1. And then it's 4 times 3 times 2 times 1. Notice all of the factors cancel except for 5. And that's what's going to happen in this expansion. So we get, the 1s cancel, the 2s cancel, the 3s cancel, 4 is not there, but they cancel all the way out. There is an n minus 2 right here. I didn't write it, but there's an n minus 2 right there. So that would cancel. The n minus 1 cancels, the n's cancel. And all that's left when I actually simplify this is n plus 1. So it turns out that the sequence n plus 1 factorial over n factorial is equivalent to the sequence of just n plus 1. That will give us the exact same sequence of numbers. Those are equivalent sequences. So when I take the limit as n is approaching infinity to determine if this guy converges or diverges, I can just take the limit as n is approaching infinity of n plus 1. But that limit, of course, as n is approaching infinity, that's just infinity plus 1. That is infinite. And therefore, it diverges, but it's diverging in such a way that it is what we say growing without bound, right? It is unbounded. It is growing without bound. It's approaching infinity. And again, when we show that a sequence diverges, we often want to know why it's diverging. So here we're explaining that it's diverging because it grows without bound. Okay, I'm going to stop. I've gone quite long on this video and I'm going to stop at that, but that is how we take a look at whether a sequence is converging or diverging.